Okay, in the previous classes, we have discussed about this convolution, or in fact, convolution sum for discrete time, linear time invariant systems. Okay, so we have concluded that if you apply a input xn to a system which is linear and time invariant, having its impulse response hn, the output yn is the convolution of xn and hn, which is given by this equation x of k hn minus k. Okay, and we have seen that how can you compute the convolution of two signals. So there are four operations. You first fold one signal, then shift it, then multiply with another and add, you get one sample. Similarly, for each sample you have to repeat all these four operations. Okay, and how we have reached to this equation of convolution? For that, what we have done, we have first expressed the sequence xn as a linear combination of weighted unit impulses. That is, it was written as summation of xk del n minus k. Okay, and then we have used the linearity and the time invariance property, and using that property we reached at this equation of yn, that is the output. Okay, now we will see how you can find the response of linear time invariant system for continuous time systems. Okay, which is given by convolution integral. And we will use a similar approach here. Okay, now for convolution integral, your input is xt. This is applied to a system which has impulse response ht, and you have to define yt. Okay, assuming that this system is linear and time invariant. Okay, so we use the same approach. We will try to first express xt in terms of unit impulses, that is delta t. Okay, and how you can do in this case, in the discrete case, what we have done, we have taken a sequence xn. Suppose this is my original sequence. So I have expressed it as sum of different sequences which are, you can say, scaled unit impulses. Okay, so this impulse I have written as x0 into delta n. Okay, because delta n is 1 and x0 is the first sample at n is equal to 0, so multiply with delta n, you will get this pulse. Then second, we have shifted this delta n by 1, delta n minus 1, and multiply with x of 1, so you get the next value. Similarly, this is x2 into delta n minus 2 and so on. Okay, and when we have added them together, what you got, x0 delta n plus x1 delta n minus 1 plus so on. Okay, this is an alternate representation of the same signal in terms of weighted unit impulses. Any discrete signal can be decomposed like this. Okay, which was then expressed in the form of a series, that is xk delta n minus k summation over k. Okay, now we use the same approach for the continuous time signals. In fact, for continuous time signals, the convolution integral is somehow a bit difficult to understand. That is why we have started with the discrete case first. It is easy to understand in the discrete case. Okay, now in the continuous time signal, in place of xn, you have a signal, input signal is xt. Okay, So any signal you can take. Suppose this is my signal. Okay. Now what we try to do, we try to express this xt again in terms of unit impulses, that is delta t. Okay. And how we do that, we basically use a staircase approximation of xt. That is, I sample this signal, suppose at t is equal to 0, and I keep it constant for some time, maybe delta. Okay. Then at t is equal to delta, I sample the next value of the signal and keep it again constant up to 2 delta. Then at 2 delta again sample the next value and keep it constant up to 3 delta. Okay. And at 3 delta again sample the next value, keep it constant for again a time period of delta, and so on, like this. Okay. So this staircase approximation, this I denote will suppose x cap t. Okay, which is a approximation of the original pulse xt. Okay. Now how you can express x cap t? Okay, for that we again use your unit impulse signal, and in the unit impulse when you have defined, we have defined first a approximation of ideal impulse, that is delta del t, which was a function which has a height of 1 by delta and a width of delta. The area is 1. Okay. And your delta t, the ideal impulse, was the limiting case of this pulse when del approaches to 0. Okay. Now how can I express the staircase function in terms of this pulse? Okay. So what I do is that, suppose at x0 I first define delta del t, which is this function 1 by del and del. Okay. And if I multiply this signal xt with this pulse, okay, what I will get, only this much portion of the function, and the amplitude of this, that is x0 at t is equal to 0, will be scaled by 1 by delta. Okay. It means this amplitude, if you multiply xt with del t, what you are going to get is, because this height is 1 by delta. Okay. And when you multiply this function with this function, its amplitude values will be scaled by 1 by delta. So you will get the same function like this, but this value will be now what? It will be x0 into 1 by del, isn't it? Up to del. Okay. But since we want this straight line, this function, okay, and for this function I want my approximation to be like this first, then I want to get next pulse. So I am trying to represent this pulse. Okay. It means this should remain at x0 between 0 to delta. Okay. And how it will happen? It will happen if I multiply this again with delta. If you multiply this with delta, your delta is 1 by delta, so 1 by delta into delta will become 1, and xt, and at t is equal to 0, so it will remain constant. Okay. It means this portion, it is basically x of 0 into delta del t multiplied with del. Okay. So between 0 to del. Similarly, when you want to get the next pulse, this one, so you have to shift this pulse by delta to the right. Okay. It will be shifted to here. This will become delta now. And the height is again 1 by del. Now if you multiply x1, that's delta. This is point. At this point, the signal has a value x of del. So if I multiply x of del with del t minus del into del, I will get the second pulse. Is it? Because delta t minus tau is basically shifted in time by delta, and if you multiply this with delta, this height becomes 1, and 1 multiplied with x of delta will remain constant between this period. Okay. Similarly, the next pulse, this one, for this you have to shift it by 2 del now. Okay, this is x of del of t minus del. This pulse is del of t minus delta t minus this is delta del, and so on. Okay, so the next third pulse I can write it as x of 2 del into delta t minus 2 del into del. Okay, like this. Similarly, next pulse, it will be x of 3 del into delta t minus 3 del into del, and so on. Okay, so when you add all this together, you will get this function, which is a staircase approximation. Okay, it means this x cap t, how I can write it? I can write it as x cap t is equal to x0 delta del t times del plus x of del delta del t minus del into del, and so on. Or you can write in the form of a series again, summation of x of k times del delta del t minus k del into del. X cap t. Okay, now so in this case, in case of discrete time, there is no approximation, it is exactly the linear combination of weighted unit impulses. But for the continuous time case, we have taken approximation of the input signal first using x cap t, and this x cap t is now expressed as a linear combination of impulses, not ideal impulses. These are again delta del t, which are the approximations of unit impulses. Okay, so now suppose this signal is my input to the system. Okay, so I take now xt is approximated by x cap t, which is given by x of k delta del t minus k delta into del. Okay, and we have seen that how we got this approximation. Okay, we have basically taken a staircase approximation of input signal, and so on, similar to the left side. Okay, this representation is for this signal. This one, this is xt, this is my x cap t, and this is for this function, this approximation. Okay, and in this function you will see that as xt is nothing but x cap t, in the limiting case del approaches to 0. So if this pulse width, if this is del, 2 del, 3 del, if this becomes very small or negligible, your x cap t will converge to xt. Okay, it means now using this approximation, we first find the output of the system, which is not the actual output. This is also approximation of the output, because input is approximated, your output is also approximated. And if you take the limiting case here, when del approaches to 0, in that case you will get the actual output. Now what is output due to this? Again, using the linearity and the time invariance property, you can say that x of k delta is nothing but it is a constant. What is the response of delta del t minus this function? If ht is the impulse response of the system, it means if input is delta t, output is ht. This is what is impulse response. Now if the system is time invariance, so if you shift the signal in time by suppose delta, your output is also shifted by the same time. This is what is the LTE system. Okay. And another property that you have is linearity, because since this is a linear combination of different weighted pulses, so we can add their individual outputs. So first is x of k del, or I can also write this equation as, suppose you can, if you expand this equation, this becomes x when k is 0, x0 del t. Okay, then x of del del t minus del and so on. So the system is linear. Your output I cap t is the output due to this plus output due to this plus so on. Okay. So what is the output due to this? X0 is constant. So this will be my X0, and delta del t del. This will be h of del t into del. Okay. Again, since I am using approximation for the unit impulse, I have to use approximation for its impulse response also. Okay. It means ht is basically when del approaches to 0, your h of del t converges to ht. Similarly, next is your x of del, and this is now where we use the time shifting property. You will get h of del t minus del into del. The next will be x of 2 del h of del t minus 2 del into del, and so on. Okay. Or you can simply write in the form of the same equation, a from minus to plus infinity x k del h of del t minus k del into del. This is your approximated output. Okay. And what will be the actual output? Yt. Now yt is your limit del approaches to 0 y cap t. Okay. Because when del approaches to 0, x cap t converges to xt. So as a result, your output y cap t will converge to yt. Okay. It means in this equation, what basically we are doing, we are expressing this input signal first as a linear combination of different pulses. So this pulse, then second delta t, then third delta t, and so on. So you're finding what is the output due to this portion only. Then what is the output due to this? What is the output due to this, this, and this? Then we are adding them together. Okay. But when the delta approaches to 0, this pulse becomes delta del t. It converges to delta t, the ideal impulse, when del approaches to 0. Okay. It means in that case, in this staircase approximation, it will become basically a continuous function, that is xt. Okay. So what you will get in the output yt in that case, when your delta approaches to 0, this x of k del, it becomes a continuous parameter. Okay. And this summation will converge to a integral. So you will get integration from minus to plus infinity x of tau h of t minus tau d tau. Okay. This is what is called as convolution integral. Okay. Now h of, in this equation, in the h I have removed this subscript delta, because now when delta approaches to 0, this becomes the actual impulse response h of t. So this equation is called as your convolution integral. Okay. So it gives you the response of a linear time invariant system using its impulse response ht. So if you know the ht of any system, So if you apply any input to the system, your output will be given by this equation, the convolution integral. Okay, and you can see that these two equations, they are almost analogous in continuous and discrete time. In the continuous time, you have yn, which is equal to summation of x of k h of n minus k, summation over k. In continuous time, we have yt, which is integration of x of tau h of t minus tau d tau. Okay, so the only difference is in the variables, and the summation is replaced with integration. Otherwise, the process for finding the convolution is same. So you have to again, suppose if you want to find this yt for any value of t naught, yt naught, what you will get? You will get x of tau h of t naught minus tau d tau. Okay, so again you have to express the functions. Like in this case, what we have done, we have first expressed the function in terms of k, that is xk, and then second was h of k, and then we have folded it, it becomes h of minus k. Then h of n minus k was basically shifting, either shift to the left or to the right by n, depending upon whether n is positive or negative. Then we have multiplied this with this. Okay, you get a multiplied sequence, which is x of k h of n minus k, and then all those samples, they were added together, you will get yn. Okay, so fold, shift, multiply and add. This is what we have done here, and the same will be done here. Now your signal xt and ht will be first represented in the form of tau. You have to write one function as x tau, another function will be h of tau. Then h of t naught minus tau you have to compute. So for that you have to first fold it. Suppose this is my x of tau, h of tau. So I have to first find h of minus tau. So for that I have to fold it to become h of minus tau. Then I have to find h of t naught minus tau. It means it is shifted by t naught to the right or left, depending upon whether t naught is positive or negative. So h of t naught minus tau will be the same function, but will be shifted by t naught. If t naught is greater than 0, it is shifted to the right. If it is less than 0, it is shifted to the left. And then you have to multiply these two signals, x tau and h of t minus tau, and then you have to integrate. You will get the output. Now there is one difference in this. When you find the convolution for discrete time, it is very simple. You have to find the output using sample by sample. You first find for n is equal to 0, then n is equal to 1, then 2, 3. Okay, so in one case you fold, then shift by 1, multiply, add. Then again fold, shift by 2, multiply, add, and so on. Now in this case, since time is continuous, you cannot find these values. So what you do in this case, you have to find the time limit for t for which this integration remains constant. Okay, so within that time period you have to find the value of yt. Okay, we will discuss many examples on this because this is somehow more important and also confusing, so I will concentrate on this in more detail. But the concept is that when you find the convolution for the two signals, you have to find the time limits within which this product remains constant. Okay, like suppose if I take two functions, this is one function, another function is supposed like this. Okay, if I multiply these two functions and integrate, so what I will do? I will do integration by parts, because this function has two different equations. From 0 to this time it has one, it is linear, then it is constant. If you multiply them two, between these 2 points, 0 to suppose any time t naught, I can integrate them, multiply and integrate them once. And beyond this t naught, this function takes a different equation. So you have two time limits, 0 to t naught and t naught to maybe up to plus infinity, like this. Okay, And similarly, when we have discussed in the convolution sum, we have discussed some properties. I will repeat those properties here. In fact, there was some confusion in the previous lecture. We have commutative property. So commutative property says that xt convolution with ht is same as ht convolution with xt. Okay. It means the role of input and the impulse response that can be interchanged. So either in xt is input to the system having an impulse response ht, you are getting output yt, or you can take ht as input to the system with impulse response xt, your output will be same. This is what is commutative property. Okay. And the second property was associative, in which you have x of t convolution with h1t convolution with h2t. It is equal to xt. First convolve this with h1t, then convolve this entire with h2t. And from this property we have concluded that when the two systems they are connected in cascade, their overall impulse response is the convolution of the two impulse responses. So this is h1, this is h2. So this can be replaced with a single system where the impulse response is the convolution of h1 and h2t. This is what is associative property. Okay. And the third was distributive, which says that xt convolution with h1t plus h2t is equal to convolution of x1t with h1 plus convolution of x1 with h2t. Okay, and this property says that when the two systems they are in parallel, their impulse response is added together. So if it has impulse response h1, it has h2, the overall impulse response of the system is h1 plus h2. Okay, and then we have discussed one more thing, that if the system is linear and time invariant, other properties of the system can be, you can simply discuss the other properties by seeing its impulse response. Okay, so first was it was memoryless. For discrete case I will take here, and then for continuous case I will repeat here. For discrete case you have yn, which is equal to summation of h of k x of n minus k. For continuous time now you have yt, which is the integration of h of tau x of t minus tau d tau. Okay, so for memoryless system what we have done here, that the output of the system should depend upon that time only. It means yn should depend upon xn, and that will happen only if xn is in the form of impulse signal delta n. Okay, sorry, not input, this hn. If hn, the impulse response of the function, is in the form of k delta n, that is that it has only value at n is equal to 0. Okay, otherwise you will get the present and the past values from input. So for a system to be memoryless, its impulse response should be a scaled impulse signal. It can be delta n, it can be 2 delta n, 3 delta n, whatever it is, but it should be delta n. And the same is the case here. If your h of t should be equal to k times delta t, the system is memoryless. Okay, the second was causality property. For causality what we have done here is that h of n should be 0 for n less than 0. If the impulse response is 0 for n less than 0, the system is causal. Okay, and why it is so? Because if h of n is 0 for n less than 0, you are not getting the future values of the output from this equation. Okay, if you are getting, if there is any, you can say, signal non-zero value for n less than 0, you are getting the future value, that is x of n plus 1, x of n plus 2. From this it will become anti-causal. And the same case will be here for causality. Your h of t should be 0 for t less than 0 for a system to be causal. Okay, because if t for t less than 0, if it is not 0, you are again getting here the positive values of x, the future values of x, x of t plus 1, t plus 2, and so on. This will become non-causal. And the third was your invertible. So for that, what we have done, that if the two systems h1n and h2n, if they are invertible, it means if you apply here input xn, the same output you will get here. But since these two are in cascade, h1 and h2 are in cascade, so their impulse response is nothing but the convolution of the two responses. It means for this system to be a invertible system, this must be delta n. Okay, because the convolution of xn with delta n is again xn, and the same is the case here. So if one system with h1t, if it has an invertible system with impulse response h2t, in that case this will form an invertible system only if the convolution of h1t and h2t is equal to delta t. This is for invertibility. Okay, and the third last one was the stability. For stability, or for a stable system, we have discussed that h of n, summation of h of n should be finite. And in this case, for stability, the integration of h of t should be finite. Okay, so if the impulse response of the system is absolutely integrable, we say the system is stable. If it is absolutely summable in the discrete case, it is stable. Okay, so in the previous class I have somehow related it to the Z transform and the Fourier transform, and you may not be able to understand. Okay, anyways, when we will discuss the Fourier series and the Z transforms, we will come to this issue of stability again there. Okay, so in the next class we will see how to find the convolution of two signals in continuous time.